And now in this lecture we'll find out the radius of the small circle. In the drawing we have a right triangle, triangle ABC. We know that the side AB of this right triangle ABC equals to 6 units in its length, side BC equals to 8 units in its length. Inside this right triangle we have this small circle, and we also have this semicircle, and our mission is to find out the radius of this small circle. So first of all, we'll implement the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABC is AC, so the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I'll write it down. Here by PT is the version for Pythagoras theorem. So AC squared, the square of the hypotenuse, must be equal to AB square plus BC square. To begin, in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total we should find out that AC square equals to 36 plus 64. 36 plus 64 equals to 100. So AC square equals to 100. We take a root out of this equation and get that the hypotenuse AC is equal to the square root of 100, that is 10. The hypotenuse AC equals to 10 units in its length. So I already know AC equals to 10. Here you can implement rule 2. If you focus on this convex point A, from this convex point A, we have two tangents to this semicircle, tangent AB, and also this tangent will define the point of tendency of tangent AC with this circle, this point as point H. So the second tangent to this semicircle is tangent AH. And according to rule 2, they must be equal to each other. So AB equals to AH according to rule 2. So I write it down. AB equals to AH according to rule 2. Actually, rule 2 states that the length of two tangents from a convex point to a circle are equal. Therefore, the length of tangent AB must be equal to the length of tangent AH. But AB equals to 6 units according to what is given as the question, so I can write here that AB equals to 6, and for this equation 6 equals to AB equals to AH, we derive that AH also equals to 6 units in its length. Actually, this is 9/7 edge or tangent edge. That is equals to 6 units in its length. What is the length of edge C? Edge C equals to AC minus AH. Again, edge C equals to AC minus AH. AC is the opposite, AC is 10, AH is 6, so edge C equals to 10 minus 6, that is 4. 10 minus 6 is 4. In the next step, we define the center of this small circle. This point is point P. We define the center of this semicircle. This point is point Q. We define the point of tendency of this small circle with tangent AB. This point is point N. We define the point of tendency of tangent AC with this circle. This point is point K. We define the touching point between this small circle and this big semicircle. This point is point T. In the next step, we join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is the point of the semicircle itself. Therefore, QH is the radius of this semicircle. We define the radius of this semicircle as B. Therefore, QH equals to B. This is the radius of the semicircle. So here we can implement rule 2. According to rule 2, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So we have here the radius QH of this semicircle is drawn to point H, that is the point of tendency or tangent AC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay. This is angle C. Angle C is a common angle that belongs to both the big right angle ABC, and angle C also belongs to the small right angle HQC. So we define the size of this angle. Angle C is alpha. And we focus on this right small triangle HCQ. In triangle HCQ, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the big right angle ABC. The big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus alpha. So I write it down. In the next step, we prove that the right big triangle, triangle ABC, is similar to this right small triangle, triangle HQC. So I write it down. The right big triangle ABC is similar to this right small triangle HCQ. So why the big right triangle ABC is similar to this right small triangle HCQ? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC in the right big triangle ABC. And it is equal to this angle, that's actually angle QHC in a small right triangle HCQ. So I put again, actually found out that angle ABC in the big right triangle ABC equals to angle QHC in the small right triangle HCQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both angles. So if we relate to this angle, angle alpha, since it belongs to the big right triangle ABC, it will be defined as angle ACB. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle HQC, it will be defined as angle HCQ. So repeat again. This equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both angles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle BAC in the right triangle ABC, and it is equal to this angle, that is actually an angle HQC in the right small triangle HCQ. Repeat again. Angle BAC in the big right triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this big right triangle ABC are correspondingly equal to all the triangles in this right small triangle HCQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the big right triangle ABC is similar. This is the sign of similar to the right small triangle HCQ according to angle similarity rule. And for the fact that the right big triangle ABC is similar to the right small triangle HCQ, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in this right small triangle HCQ. And again, we derive the side AB in the big right triangle ABC over side HQ in the right small triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Okay. AB is 6 over HQ. HQ is the radius of this big semicircle that equals to B according to our definition. And it is equals to BC. BC equals to 8 according to what is given us the question. Over HC. HC equals to 4 according to what we already found out. So in total we actually found out that we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So in total we found out that 6 over B equals to 2. Here we multiply this equation by B and we get that 6 equals to 2B. Here we divide this equation by 2. Finally we get that B equals to 6 over 2, that is 3. So the radius of this big semicircle B equals to 3 units in its length. Write it down, B equals to 3. Here, point Q is the center of this semicircle, point B is the point on the semicircle itself, therefore QB is the radius of this semicircle, and we just right now found out that the radius B of this semicircle equals to 3 units in its length. So QB equals to 3. I write it down. In the next step, we will join points P and N together by a straight line. Point P is the center of this small circle, point N is the point of the small circle itself, therefore Pn is the radius of this small circle. That is the radius that we are looking for in this question. We'll define the radius of this small circle as A, so Pn equals to A according to our definition. Here we can implement rule 1 because we have the radius Pn is equals to A, the radius Pn is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. Again, PK is the radius of this small circle, that is equals to A. Again, the radius PK is 1 to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PK and then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if you form an external point of a circle, you will draw two tangents to that circle. Yeah. This is the common external point, point P. From this common external point, point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing those two tangents, we get the angle APB. This is angle APB. So, according to rule 15, then the angle that will be created between the two tangents, the angle is actually angle APB. This angle, its angle bisector must pass through the center of the circle. So the angle bisector of this angle, angle APB, is equals to theta, angle bisector of angle APB. The angle bisector of angle APB must pass through point O, that is the center of this circle. So whenever you draw two tangents to a circle from a common external point of that circle towards the circle, then you will create an angle, and the angle bisector of that angle must pass through point O, that is the center of the circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if you focus on this common external point, point A, on this common external point, point A, we have two tangents to this small circle, tangent AN and tangent AK. And the angle that was created by those two tangent AN and AK is this angle, angle A. Again, this is the angle A that is created by drawing two tangents AN and AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So we join points P and A together by side line, and PA will be the angle bisector of this angle, angle A. That is to say, according to rule 15, the angle bisector of this angle A must pass through point P. So I write it down. Actually found out that the angle bisector of angle A bisector of angle A passes through point P of this small circle. Point P is the center of the small circle. continue to focus on this convex point, point A. From this convex point A, we have two tangents to this semicircle, tangent AB and tangent AH. Therefore, we can implement here all 15 because the angle that is created by drawing the two tangents AB and AH is the same angle A. And according to rule 15, the angle bisector of the same angle A must pass through point Q, that is the center of this semicircle. So we join points Q and A together by straight line. So QA will be the angle bisector of this, the same angle A. Again, QA is the angle bisector of the same angle A. So again, according to rule 15, the angle bisector of this angle A must pass also for point Q. That is the center of this semicircle. So I write it down. Actually found out that the angle bisector of the same angle A passes also for point Q. The angle bisector of this angle A must pass, of course, for point A. So I write it down. The angle bisector of the same angle A passes for point A itself. For point A. In conclusion, we found out that the angle bisector of angle A passes for points A, P, and Q. Again, actually found out that the angle bisector of this angle A passes for point A, P, and Q. But we know that the angle bisector of any angle is a straight line. Therefore, and all the three points A, P, and Q are located on the angle bisector of angle A. Therefore, we can write down that points A, P, and Q are located on the same straight line. I write it down. I actually found out that points A, P, and Q are all located points A, P, and Q are all located on the same straight line. That is the straight line that is the angle sector of A. So the angle sector of A is a straight line. Again, and for we found out that points A, P, and Q are all located on the same straight line. Well, we can also say that line segment APQ is one straight line. Again, line segment APQ is one straight line. So I'm writing down, if we found out that line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. And if AQ is a straight line, it means that shape ABQ is a right angle. Again, if AQ is a straight line, it means that shape ABQ is a right angle. So if we found out that shape ABQ is a right angle, because AQ is a straight line. So in the right angle ABQ, actually, if we define the size of angle A, if we define the size of this angle A is 2 theta, then the angle bisector PA bisect angle A into 2 halves. Each half must be equal to theta. So this angle is theta and this angle is also theta. Likewise, the angle bisector QA also bisect the same angle A into 2 halves, and each half must be also equal to theta. So in the right angle ABQ, this is angle theta, but angle theta is a common angle that belongs to both angles. Why? Because angle theta belongs also to the right small triangle A and P. In the next step, we focus on the right big triangle ABQ. In the right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on this right small triangle A and P. In the right small triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the right big triangle ABQ is similar to this right small triangle A and P. So I write it down. So I prove that the right big triangle ABQ is similar to this right small triangle ANP. So why the big right triangle ABQ is similar to this right triangle ANP? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ in the right big triangle ABQ. And it is equal to this angle. It's actually angle ANP in the small right triangle ANP. And again, I should found out that angle ABQ, the big right triangle ABQ, equals to angle ANP, the small right triangle ANP, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So we can find out that angle theta equals to itself is a common angle that belongs to both triangles. So actually, if we relate to angle theta as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And angle theta equals to itself. So if we look at this angle theta as it belongs to this right small triangle ANP, it will be defined as angle NAP. Okay, again, we actually found out that angle BAQ in the right big triangle ABQ equals to angle A and actually this equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle AQB, and the right big triangle ABQ, and this equals to this angle, that is actually angle APN, and the right small triangle ANP. Because again, actually found out that angle AQB in the big right triangle ABQ equals to angle APN in the small right triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the triangles in this big right triangle ABQ are correspondingly equal to all the triangles in this right small triangle ANP. Therefore we proved that those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the big right triangle ABQ is similar, this is the sign of similar, to the right small triangle ANP according to angle similarity rule. And from the fact that the big right triangle ABQ is similar for this one right triangle A and P, we will derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB equals to 6, so we substitute AB by 6 over AN. AN is the missing side, so we leave it as it is. And it is equals to BQ. BQ equals to 3, according to what we already found out. It is actually the radius of the big semicircle. So we substitute BQ by 3 over NP. We already found out actually is actually HP. Actually, over NP, this NP equals to A. This is NP, and NP equals to A. A is the radius that we are looking for. That's actually the radius of this small circle. So in conclusion, we found out that 6 over AN equals to 3 over A. Here we cross multiply this equation, and we get that 6A equals to 3AN. 6A equals to 3AN. Here we divide this equation by 3, and finally we get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. In conclusion, we shall find out that this is the missing side AN, that is equals to 2N. The missing side AN equals to 2A. So here we know that AB equals to 6, AN equals to 2A, therefore the missing side NB must be equal to AB minus AN. The missing side NB must be equal to AB minus AN. AB is 6, AN is 2A, so in total the missing side BN must be equal, or NB must be equal to 6 minus 2A. In the next step, we do a construction, that is to say, from the center of this small circle, that is to say, from point P, we go perpendicular on BQ. Again, from point P, we go perpendicular on BQ. So actually, this again equals to 90 degrees, and this again equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point L. Actually, by doing this construction, we can do quadrilateral APLQ. This is quadrilateral LPLQ. Inside quadrilateral NP, actually it is quadrilateral NPLB. Inside quadrilateral NPLB, we have 1, 2, 3 right angles. So the sum of three right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So actually, inside quadrilateral NPLB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we evaluate to quadrilateral NPBL is a rectangle because it has 4 right angles. So write it down. This is quadrilateral NPBL and it is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle NPLB, side NP must be equal to side BL. Again, side NP must be equal to side BL. But NP is A, therefore BL must be also equal to A. Likewise, according to the same rule, in the same rectangle NPLB, side BL must be equal to side MB. Okay, but NP equals to 6 minus 2A, so PL must be also equal to 6 minus 2A. PL equals to 6 minus 2A. What is the length of line segment LQ? LQ equals to BQ minus BL. Again, LQ equals to BQ minus BL. So LQ equals to BQ, that is 3, minus BL, that is A. So in total, BQ equals to 3 minus A. This is side LQ. That equals to 3 minus A. Repeat again. This is side LQ. LQ equals to BQ minus BL. So LQ equals to BQ, that is 3, minus BL, that is A. So in total, LQ equals to 3 minus A. What is the length of side PQ? Actually, we have an external length between this small circle and this big semicircle, that is to say they are touching each other externally at point T. And whenever you have an external length between two circles, you can implement rule 10. I'll repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass for their touching point. So in the drawing we have two circles. Those two circles have an external length between them, and this point P. This is to say they are touching each other externally at this point P. The center of this small circle is at point M. The center of this big circle is 0 at point O. and the straight line that connects the centers together is of course the straight line MO. So this straight line MO must pass through point P, this is their touching point. Okay, so we can actually implement all 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. The attachment point is at point T. The center of this small circle is here at point P. The center of the big semicircle is here at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, PQ must pass through point T. Again, according to rule 10, PQ must pass through point T. Or PTQ is one straight line. Again, PTQ is one straight line according to rule 10. If PTQ is one straight line, it means that PQ is also a straight line. And therefore the length of PQ must be equal to PT plus TQ. So I write it down. The length of PQ in total, it must be equal to PT plus TQ. So PQ equals to PT. PT is 8, is the radius of this small circle, this is the radius that we are looking for in this question, plus TQ. TQ is the radius of this semicircle, is equals to 3. So in total we found out that PQ equals to A plus 3. Okay, PQ equals to A plus 3. In the next step, I'll copy this green right triangle PLQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PLQ. PL equals to 6 minus 2A. This side LQ equals to 3 minus A. And finally, the opposite PQ equals to A plus 3. So actually, this is the right green triangle PLQ that I got from the original drawing. According to the Pythagoras theorem, in this right triangle PLQ, PQ square equals to PL square plus LQ square. Again, PQ square equals to PL square plus LQ square. Again, PQ square equals to PL square plus LQ square. Repeat again. According to the Pythagoras theorem in the right triangle PLQ, PQ square, that is the square of the hypotenuse, must be equal to PL square plus LQ square. PQ is A plus 3, therefore PQ square is A plus 3 square. And it must be equal to PL square. PL is 6 minus 2A, therefore PL square is 6 minus 2A square. Plus LQ square. LQ is 3 minus 8, therefore LQ square is 3 minus 8 square. In conclusion, we found out that in the right triangle P and Q, A plus 3 square equals to 6 minus 2A square plus 3 minus A square. We will open the brackets on both sides of this equation and we'll get that A plus 3 square equals to A square plus 3 square, that is 9, plus 2 times A times 3, that is 6A, and it is equals to 6 minus 2A square. 6 minus 2A square equals to 6, well, that is 36, plus 2A square, that is 4A square, minus 4 times 6 times 2A, minus 4 times 6, minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A. And also here, 3 minus A square. 3 minus A square is 3 square, that is 9. Again, 3 square is 9. Plus A square. Minus 2 times 3 times A is minus 6A. So here we have A square on both sides of the equation, so A square will get cancelled. And we also have 9 on both sides of the equation, so 9 also will get cancelled. After you cancel 9, in this side of the equation we left only with 6A. In the other side of the equation we have 36 plus 4A square, and we have minus 24A minus 6A is minus 30A. In conclusion, we found out that 6A equals to 36 plus 4A square minus 30A. So here we subtract 6A from this equation and you get that here 6A minus 6A is 0 equals to 36 plus 4A square minus 30A minus 6A is minus 36A. So here we divide this equation by 4. Again, we divide this quadratic equation by 4 and we get that 4A square over 4 is A square minus 36A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion, we actually found out that a squared minus 9a plus 9 equals to 0. So actually this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of a, again a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c or 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we're looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And finally, the coefficient c equals to 9. The only thing that is left to do is to put the data for our specific quadratic equation inside this general formula, and we find out the value of the values of a, because x equals to a. We'll do it now, and we get that again x equals to a, so it is a equals to minus b, b equals to minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, plus minus 4 times ac. So it is minus 4 times a is 1, so minus 4 times 1 is minus 1, times c, that is 9, so minus 4 times 9 is minus 36. So inside the root we left only with 81 minus 36 over 2a. A is 1, so 2 times a is 2. So we can find out that a equals to 9 plus minus 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a is the radius that we are looking for in this question. It's the radius of the small circle. So a equals to, according to the first solution for a equals to 9 plus square root of 45 over 2. Actually, this expression 9 plus square root of 45 over 2 is definitely greater than 3. But the radius of the small circle A cannot be greater than 3. Why? Because of the fact that the radius of this semicircle B equals to 3, and from the drawing it is very easy to see that the semicircle is much more bigger than this small circle. Therefore, the radius of this small circle must be less than 3, because 3 is the radius of the big semicircle. So the option that the radius A equals to this expression that is greater than 3 is the incorrect option. So we left only the second solution for A. The second solution for A is that A equals to 9 minus, here we have square root of 45 is 9 times 5, and square root of 9 is 3. So this expression in total equals to 9. So the square root of 9 is 3, so this expression in total equals to 3 times square root of 5 over 2. So the area of this green circle, this small circle equals to either 9 minus 3 times square root of 5 over 2 units in terms of numbers. The radius of this small circle A equals to 1.146 units. And this is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the radius of this small circle. So, in the drawing we have a right triangle. In the drawing we have a right big triangle. We know that side AB of triangle ABC equals to 6 units in its length, side BC equals to 8 units in its length. This is angle ABC, this is a right angle. And inside this right big triangle we have this small circle and also this big semicircle. The semicircle touch each other externally at point T. Again, our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so leave it as it is. So AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, we found out that AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We took out this equation, and finally found out that the length of the hypotenuse AC it is equals to 10 units. This is the hypotenuse AC of the right angle ABC, and it is equals to 10 units in its length. So here we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So if you focus on this common external point, point A, from this common external point A, we have two tangents to the big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. Repeat again. AB equals to AH according to rule 2. But it is given us a question that AB equals to 6. So I can write here that AB equals to 6, and from this equation 6 equals to AB equals to AH, we derive that AH also equals to 6 units in its length. So here, what is the length of line segment HC? From the drawing it is very easy to see that HC equals to AC, the hypotenuse AC minus AH. Again, AC minus AH equals to AC. So HC equals to AC, that is 10, minus minus AH, that is 6. 10 minus 6 is 4. So HC equals to 4 units in its length. In the next step, we defined the relevant points to this question with letters. We defined the center of this small circle, this point as point P. We defined the center of this big semicircle, this point as point Q. We define the point of tendency of tangent AB with this small circle, this point is point N. We define the point of tendency of tangent AC with this small circle, this point is point K. And also define the touching point of this small circle with this big semicircle, this point is point T. So in the next step, we join points Q and H together by a straight line. QH is the radius of this semicircle. The radius QH is known to point H, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is known to the point of tendency, then tangent AC must be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. So actually, this is angle C, and it is a common angle that belongs to both triangles. Angle C belongs to the right big triangle ABC, and this the same angle C also belongs to the right small triangle HCQ. So we define the size of this angle C is alpha. So in the right triangle CHQ, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle ABC, the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Okay, so in the next step, we prove that the right big triangle ABC is similar to this small right triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually proved that all the angles in the right big triangle ABC are correspondingly equal to all the angles in the right small triangle HCQ. Therefore, the big right triangle ABC is similar to this right small triangle HCQ according to angle similarity rule. And again, if we found out that the big right triangle ABC is similar to the small right triangle HCQ according to angle similarity rule. And from the fact that the big right triangle ABC is similar to the right small triangle HCQ, we derive that the following relationship exists between their sides. We derive that side AB in the right big triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC or side HC in the small right triangle HCQ. Read again. We will derive that AB or AHQ equals to BC or BH. Okay. AB is 6, HQ equals to B, it is the radius of this big semicircle. So HQ is B, BC is 8, and HC is 4. So in conclusion, if we found out that 6 over b equals to 8 over 4, 8 over 4 is 2. So found out actually that 6 over b equals to 2. We multiply this equation by b. So 6 equals to 2b. We divided this equation by 2. We finally found out that the missing radius b is equal to fluidity in its length. This is the radius b of this semicircle, and this is equals to fluidity in its length. QB is also the radius of this big semicircle, therefore it is equal to fluidity in its length. In the next step, we join points P and N together by set line. Pn is the radius of this small circle. We define the radius of this small circle as A. We have the radius Pn, that is 1 to point N, that is the point of tendency of tangent AB with this small circle. Whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. This is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay. So here we join points P and K together by set line. PK is the radius of this small circle. That equals to A according to our definition. The radius PK is 1 to point K, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I presented to you rule 15, and we implemented rule 15 in our drawing. According to rule 15, if from an external point of a circle you draw two tangents to that circle, here, this is the external connection point P. For this connection point P, we have two tangents to this circle, tangent PB and tangent PA. By drawing the two tangents we created here, angle APB. This is angle APB that is created by drawing the two tangents PA and PB. Okay. So the angle that will be created between the two tangents, the angle is angle APB. This angle, its angle bisector must pass through the center of the circle. So the angle bisector of this angle, angle APB, must pass from point O, that is the center of this circle. So whenever you draw two tangents from a common point of a circle to a circle, then you will create an angle. The angle bisector of the angle that was created by the two tangents must pass for the center of the circle. This is according to this rule, rule 15. So we can actually implement rule 15 in our drawing. One, in our drawing, if we focus on this connection point A, for this connection point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing those two tangents we created here, angle A. Again, this is angle A that was created by drawing tangent AK and tangent AN to this small circle. According to rule 15, the angle bisector of angle A must pass from point B, that is the center of this small circle. Again, according to rule 15, the angle bisector of angle A passes from point B, that is the center of the small circle. Likewise, we continue to focus on this common standpoint, point A. From this common standpoint, point A, we have tangent AB and tangent AH to this semicircle. By drawing those two tangents, we created here the same angle, angle A. Now, according to rule 15, the angle bisector of this angle A must pass from point Q, that is the center of this semicircle. Again, according to rule 15, the angle bisector of this angle, angle A, that was created by drawing the two tangent AH and edge AB. The angle bisector of this angle A must pass through point Q, that is the point, the center of this semicircle. Okay, again, we should find out that the angle bisector of angle A also passes for point Q. Okay? So, but the angle bisector of angle A also must pass also from point A, it's obvious. So in conclusion, we found out that the angle bisector of this angle A must pass through points A, P, and Q. And again, the angle bisector of angle A must pass through point A, P, and Q. Okay. But we know that the angle bisector of any angle is a straight line. Again, the angle bisector of any angle is a straight line, and the angle and the 3 points must pass points A, P, and Q are part of the angle bisector that is a straight line. Therefore, the 3 points A, P, and Q are located on the angle bisector of angle A. So, all the 3 points A, P, and Q are located on the same straight line. Therefore, we can write down that, again, we should found out that points A, P, and Q are located on the same straight line. And therefore, APQ is one straight line. Again, line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. If AQ is a straight line, it means that shape ABQ is a right triangle. If AQ is a straight line, it means that shape ABQ is a right triangle. Again, shape ABQ is a right triangle. And if we define the size of angle A is 2 theta, then the angle bisector PA bisects angle theta into 2 halves. Each half must be equal to theta. Likewise, the angle bisector QA of the same angle, angle A, bisects angle A into 2 halves. Each half equals to theta. Therefore, in conclusion, we can say that this is angle theta, that is a common angle. Angle theta belongs to the small right triangle A and P, and this angle theta also belongs to the big right triangle ABQ. So in the big right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, if you focus on the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus theta. In the next step, we proved that the right big triangle ABQ is similar to this right small triangle A and P. So why the big right triangle ABQ is similar to this right small triangle A and P? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself, it's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So if we prove that all the three angles in the right big triangle ABQ are correspondingly equal to all the three angles in this right triangle A and P, therefore those two right angles are similar to each other according to angle similarity rule. So okay, again, if we found out that the right big triangle ABQ is similar to the right small triangle A and P according to angle similarity rule. Okay. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. I'll repeat again. We derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle NP. AB 6, AN is the missing side, so we leave it as it is. BQ is the radius of this semicircle that is free, and NP is A. It is the radius that we are looking for, the radius of this small circle. So we should find out that 6 over AN equals to 3 over A. Here we cross multiply this equation and finally found out that 6A equals to 3 times AN. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So the missing side AN equals to 2A units in its length. This is the missing side AN. This equals to 2A units in its length. We know that AB equals to 6, AN equals to 2A, therefore the missing line 7 and B equals to AB minus AN. AB is 6, AN is 2A, so in total NB equals to 6 minus 2A. This is 9 segment NB, this equals to 6 minus 2A. From this point P, that is the center of this small circle, we do perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point A. By doing this construction, we deduct quadrilateral P and BL. In quadrilateral P and BL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So in size quadrilateral NPBL we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to this quadrilateral NPBL is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle NPBL, side NP must be equal to the opposite side BL. But NP is A, therefore BL must be also equal to A. Likewise, according to the sum rule, in the sum rectangle NPBL, side NB must be equal to the opposite side PL. But NB is 6 minus 2A, therefore PL must be also equal to 6 minus 2A. What is the length of LQ? From the drawing it is very easy to see that LQ equals to BQ minus BL. Again, LQ equals to BQ minus BL. So LQ equals to BQ, that is 3, minus BL, that is A. So in total, LQ equals to 3 minus A. So in conclusion, we found that PL equals to 6 minus 2A, LQ equals to 3 minus A. What is the length of PQ? We find out the value of PQ or the length of PQ by implementing rule 10 in our drawing. In our drawing we have this small circle touches this big semicircle at this point C. So in our drawing we have here an external notch between the small circle and the big semicircle. That is to say they are touching each other externally at point C. And whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. So in the drawing, we have those two circles have an external notch between them at point P. That is to say they are touching each other externally at point P. The center of this small circle is here at point M. The center of this big circle is here at point O. And the straight line that connects the centers together is of course the straight line MO. And this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and the big semicircle, that is to say they are touching each other externally at point T. Therefore we can implement rule 10. According to rule 10, we know that the center of this small circle is 0 at point P. The center of this big semicircle is 0 at point Q. And the straight line that connects their centers together is of course the straight line PQ. The straight line PQ must pass through point T, that is the attachment point. Again, the straight line PQ must pass through point T, that is the attachment point. Or PTQ is one straight line. If PTQ is one straight line, it means that PQ is a straight line. PQ is a straight line, so what is the length of PQ? Because of the fact that PTQ is a straight line, it means that the length of PQ will be equal to PT plus TQ. Again, PQ equals to PT plus TQ. Again, PQ equals to PT plus TQ. So PQ equals to PT, that is A is the radius that we're looking for, it is the radius of this small circle, plus QT. QT is the radius of this semicircle, is equals to 3. So in total we shall find out that PQ equals to A plus 3. So the hypotenuse PQ is A plus 3. The next step, I copied this right again triangle PLQ in a new page and we implemented the Pythagoras theorem on this right triangle PLQ. Actually, this is the right triangle PLQ that according to the original domain, we have already found out that the hypotenuse PQ equals to A plus 3, LQ equals to 3 minus A, and PL equals to 6 minus 2A. According to the Pythagoras theorem, in this right triangle PLQ, PQ square equals to PL square plus LQ square. Again, PQ square equals to PL square plus LQ square. PQ is A plus 3, therefore PQ square is A plus 3 square. And this equals to PL square. PL is 6 minus 2A, therefore PL square is 6 minus 2A square, plus LQ square. LQ is 3 minus A, therefore LQ is 3 minus A square. Here we open the brackets on both sides of this equation, and finally found out that A plus 3 square equals to A square, plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, and it is equals to 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, times 2A. 12 times 2A is minus 20, minus 12 times 2A is minus 24A, and we have here plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times A is minus 6A. So here we have A squared on both sides of the equation, so A squared will get cancelled, and we have 9 on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6A, in the other side of the equation we have 36 plus 4A squared, and we have minus 24A minus 6A is minus 38. So in conclusion, we should find out that 6A equals to 36 plus 4A squared minus 38. Here we subtracted 6A from this equation and finally found out that in this side of the equation we left is 0. In the other side of the equation we have 36 plus 4A squared, and minus 38 minus 6A is minus 36A. So in conclusion, we found out that 36 plus 4A squared minus 36 equals to 0. Here we divided this equation by 4 and finally found out that 4A squared over 4 is A squared, minus 36A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion, we found out that A squared minus 9A plus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In the general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a. So x equals to a, the coefficient a is 1, the coefficient b is minus 9, and the coefficient c is 9. The only thing that is left to do is to put the data for our specific quadratic equation in this general formula for x, and we find out the value of the values of a, because x equals to a. A is the radius that we are looking for. This question is the radius of this small circle. So we did it and found out of a. Again, x equals to a, so, and it is equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c, that is 9, minus 4 times 9 is minus 36. So, if we already found out that inside the root we have 81 minus 36, divided by 2a. A is 1, so 2 times a is 2 times 1, that is 2. So actually found out that a equals to 9 plus minus 81 minus 36 is 45. So inside the root we left only with 35 divided by 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2, that is greater than 3. This expression definitely is greater than 3. So we shall find out that the radius of this small circle A is greater than 3 units. But it is impossible that the radius of the small circle is greater than 3 units. Why? Because of the fact that the radius of the semicircle, that is much bigger than the radius of this small circle, the radius of this big semicircle equals to 3 units in itself. And therefore the radius of this small circle must be less than 3 units. So the radius A of the small circle will not, it is impossible that it is greater than 3. Therefore we cancel this solution. This solution is incorrect solution. And we left only with the second solution that was possible for the radius A of the small circle. The radius A, according to the second solution, equals to 9 minus, here we substitute 45 by 9 times 5, and the square root of 9 is 3. So in total, this expression equals to 3 times square root of 5 divided by 2. So according to the second solution for A, the radius A of this small circle equals to 9 minus 3 times square root of 5 over 2 units. Or in terms of numbers, the radius A equals to 1.146. This is, of course, less than 3 units. Repeat again, we found out that the radius of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, the radius A of this small circle equals to 1.146 units. Okay, thank you very much.